Between 1964 and 1998, more than 4,000 surface-to-air missiles were fired at this aircraft. Not one of them ever hit it. Not one. And the reason isn't stealth. It isn't jamming or clever electronics or luck. The Blackbird carried no countermeasures worth the name. When a missile came up to meet it, the crew pushed the throttles forward and left it behind because of what it actually was. Not a fighter, not a bomber. It carried no weapons at all. The SR-71 was a camera wrapped in the fastest airframe anyone has ever built. It cruised above 80,000 feet, higher than almost anything else could reach. It traveled faster than a rifle bullet, and it could photograph 100,000 square miles of ground in a single hour. All of it drawn up with slide rules and drafting boards by engineers who had to invent most of the technology as they went, because nothing like it had ever existed. To understand how they got there, you have to start with the day the previous answer failed. On the 1st of May 1960, a U-2 flown by Francis Gary Powers was brought down over Sverdlovsk, deep inside the Soviet Union, by a surface-to-air missile. The U-2 had been considered unreachable. It flew so high that Soviet defenses simply could not touch it. That assumption died over the Urals. Powers survived and was captured. The Soviets paraded the wreckage. The Paris summit between Eisenhower and Khrushchev collapsed within days, and relations froze. And the United States was left needing something new. Not an aircraft that flew higher. An aircraft that could not be shot down at all. Altitude alone was no longer enough. The job went to Clarence Johnson, known to everyone as Kelly, who ran Lockheed's Advanced Development Projects Division in Burbank, California. Everybody called it the Skunk Works. Johnson's team had already built the U-2. Now they were being asked for something considerably harder, on a schedule nobody thought possible. What emerged first was a single-seat CIA aircraft called the A-12, flown from a secret Nevada airfield. The SR-71 was its larger, two-seat successor built for the Air Force. But one piece of physics dictated every single decision that followed. At Mach 3, air doesn't flow past an aircraft. It slams into it. The friction heats the skin past 260 degrees Celsius, and the nose and inlets run hotter still, well beyond 300. Ordinary aircraft aluminium starts losing its strength somewhere above 120. At Blackbird speeds, it would soften like warm butter. There was only one practical material that could take that heat and still be light enough to fly: titanium. And in 1960, almost nobody knew how to build an aircraft out of titanium, for the simple reason that almost nobody ever had, which led to one of the strangest episodes of the entire Cold War. America had no reliable domestic supply of high-grade titanium ore. The world's largest producer of it was the Soviet Union. So the CIA quietly set up a web of front companies and third-party intermediaries and bought it. The Soviets sold the metal with no idea what it was for, and it was shipped west to be turned into an aircraft designed to photograph them. Then the real education started, and most of it was learned by failing. Titanium is hard, and it destroyed conventional cutting tools almost immediately. Lockheed had to develop entirely new ones from scratch. The metal reacted badly to chlorine, so parts washed in ordinary tap water developed corrosion. The factory switched to distilled water for everything. And cadmium-plated spanners, standard issue across American industry, left traces on the metal that made it brittle. Bolt heads were snapping clean off at temperature. Every one of those tools had to be hunted down and removed from the factory. By the end, roughly 85% of the finished airframe was titanium, and the team had essentially invented the manufacturing process alongside the aircraft itself. But heat did something stranger to the Blackbird than simply soften it. It made the aircraft grow. At cruising speed, thermal expansion stretched the structure by several inches along its length. The whole aircraft became measurably longer in flight than it was on the ground. You cannot build an airframe that fits perfectly cold and expect it to be a different size hot. So Lockheed did the only sensible thing. They built it to fit properly when it was hot, which meant that on the ground, cold, it didn't quite fit at all. The corrugated skin along the wings looks like a manufacturing defect. It was completely deliberate, giving the metal somewhere to expand into rather than buckling under its own heat. And it leaked. Parked on the apron, an SR-71 dripped fuel steadily onto the concrete underneath it. which alarmed almost everyone who saw it for the first time. It wasn't a fault. The fuel tanks were sealed by exactly the same thermal expansion that sealed everything else. Cold on the ground, the seams simply weren't tight. Only at temperature did they close properly, which is why Blackbirds took off carrying only a partial fuel load, climbed, accelerated until the aircraft sealed itself, and only then met a tanker in the air to fill up properly before going anywhere at all. Which brings us all the way back to the missiles. Because interception is not really a question of speed, it's a question of geometry. Against an aircraft covering more than half a mile every second at 80,000 feet, the geometry simply doesn't work. A missile has to be fired not at where the target is, but at where it is going to be. By the time it arrives at that point, the Blackbird is already gone. The energy needed to close that gap simply isn't there. So the crew's response to a launch warning was not to jink or deploy chaff. It was to accelerate and climb. Go faster, go higher, and the problem solves itself. Speed was the entire defensive system. Nothing else was needed because nothing else could keep up. But sustaining that speed for hours at a time was an engineering problem all of its own. Ordinary jet fuel would have boiled and vaporized inside a structure running that hot. So the Blackbird burned a special blend called JP7, formulated to be so reluctant to ignite that you could reportedly drop a lit match into a pool of it and watch the match go out. Excellent for a tank sitting at 260 degrees. Considerably less excellent when you actually want the engines to light. So they lit it chemically with triethylborane, which ignites spontaneously on contact with air and burns bright green. Crews could tell a Blackbird was starting by the color of the flame. The engines were a Pratt & Whitney design called the J58, and they did something no production engine has done before or since. They changed what kind of engine they were in flight. Below Mach 2, it behaved like a conventional afterburning turbojet. Above it, valves opened and began bleeding air from the compressor straight into the afterburner, bypassing the core entirely. At full speed, most of the thrust was coming from air simply being rammed through and burned, effectively a ramjet. Managing the air going in was harder still. A movable cone at the front of each nacelle slid forward and back to hold the shockwave exactly where it needed to be. Get it right and the inlet did most of the compression for free. Get it wrong and the shockwave was expelled from the inlet in a violent event called an unstart. One engine lost thrust instantly while the other kept pushing, and the aircraft slewed sideways hard enough to slam the crew's helmets into the cockpit walls. Pilots described it as being hit by a train, but the machine was only half of it. Somebody had to fly the thing. At 85,000 feet, the cockpit environment is closer to space than to normal aviation. Crews wore full pressure suits, effectively early spacesuits, and had to be helped into the aircraft by technicians. Navigation was handled partly by an astro-inertial system that tracks stars through a window in the upper fuselage, in broad daylight, because at that altitude, the sky above you is dark enough to see them. 2 men flew it, a pilot in front, and behind him a reconnaissance systems officer running the cameras, the sensors, and the navigation. The windscreen ran hot enough that pilots described warming a gloved hand against the glass. In service, they flew from a handful of forward bases. Kadena on Okinawa, where the aircraft picked up its nickname, Habu, after a local pit viper. RAF Mildenhall in England. Beale in California. They flew over North Vietnam, over the Middle East during the Yom Kippur War, over North Korea. 32 were built. 12 were lost across the aircraft's entire operational life, every single one to accident or mechanical failure. Not one Blackbird was ever lost to enemy action. On the 28th of July, 1976, an SR-71 set an absolute speed record of 2,193 miles per hour and an altitude record in sustained level flight of 85,069 feet. Both still stand for a manned air-breathing aircraft. In September 1974, a Blackbird flew New York to London in 1 hour and 54 minutes. And on its very last flight, in March 1980, delivering the aircraft to the Smithsonian, an SR-71 crossed the United States from Los Angeles to Washington in 64 minutes. So why retire it? Not because anything ever caught it. It was retired because it was extraordinarily expensive to operate, needing tankers, specialist fuel, and dedicated crews for every single sortie. And because satellites had improved enough to do much of the work from orbit without risking anyone, the Air Force withdrew the fleet in 1990, briefly reinstated a few under congressional pressure in the mid-90s, then let them go for good. NASA flew the last examples as research aircraft until 99. Nothing has replaced it, and there is something worth sitting with in that. It first flew in 1964. It was designed without computers, using a material almost nobody understood, burning a fuel that had to be invented for it, powered by engines that rebuilt their own operating cycle in midair. And more than 60 years later, the fastest aircraft anyone has ever flown is still the one they drew. If you enjoyed this story of flight, subscribe to Wings and Stories. New aviation history several times a week.